Hey everybody, today we are talking about predicting the products of chemical reactions, but we're going to focus in on some exceptions to the rules that we have created over the course of the past week. So go ahead and get out a piece of paper. You're going to want to take these notes. I'm going to do this just kind of freehand. So make sure you're taking notes so you are able to complete the predicting exceptions worksheet that is posted in week 8 of Classroom. So the first exception to what we have done pertains to decomposition reactions. Now, there are basically 3 exceptions here that we're going to talk about. So what we've talked about to this point is that if you have a compound AB, that compound is going to break down into A plus B, and you're basically going to see, are those elements that are created monoatomic or diatomic, and then you're going to balance the equation. Now, today, we're going to talk about a couple other types of decompositions that can occur. The first is called the decomposition of a ternary ionic compound. So when I say a ternary ionic compound, what I'm saying is there is going to be a metal bonded to a polyatomic ion. So an example of a ternary ionic compound is something like calcium phosphate. So in that case, calcium, Ca, is our metal, and phosphate, PO4, is our polyatomic ion. Now, calcium has a +2 charge, phosphate has a -3 charge, so we're going to put Ca3PO42 to make sure that that is balanced. Now, when calcium phosphate breaks down, it doesn't break down in the way you would think. So if I were to ask you to predict this without covering it, my guess is you would put calcium as one product and you would put phosphate as the other product. However, when you get the decomposition of a ternary ionic compound, assuming that carbonate is not the polyatomic ion, what's going to happen is calcium, the metal, is going to go grab the first nonmetal that it can. So in this case, the first nonmetal is phosphorus. So one product is going to be calcium phosphide. Now, calcium has a +2 charge. Phosphide is -3. So we're going to need 3 calciums for every 2 phosphorus atoms. And then what we're going to be left with is whatever we have left, which in this case is oxygen. And then you should understand oxygen is part of Hankel-Briff. It's diatomic, so we are going to put O2. Then you can go back and balance this equation like you always would. So regardless of what the metal is always going to grab the first nonmetal, which in this case was phosphorus, that it can. That's going to create one product, and then oxygen is going to be the other product. Now, an exception to this exception is when we have something like calcium carbonate. So calcium carbonate, calcium's +2, carbonate is -2. The problem with this example, and we've talked about this a lot this year, is when carbon is your first nonmetal. Carbon is not even truly a nonmetal. Like carbon is not going to form an ion with calcium. So in this one example, if the first nonmetal is carbon, calcium is going to skip carbon and it's going to go get oxygen. So what we're going to get is calcium with oxygen. Calcium's +2, oxygen's -2, so you get calcium oxide. And then what's left over is CO2. So you get carbon dioxide. This occurs only if you have carbonate or percarbonate or carbonite or hypocarbonite as the polyatomic in your compound. Now, the other type of decomposition reaction is the decomposition of a hydrate. Now, we haven't covered what a hydrate is yet this year, but a hydrate is basically an ionic compound that has water bonded to it, or some number of waters bonded to it. So if I tell you that we have copper 1 phosphide hexahydrate. So that is a substance, copper 1 phosphide hexahydrate. Now, hydrate refers to water. Hexa, you should already know what that prefix means. So what we basically have here is we have copper 1, which is +1, with phosphide, which is -3. So that's Cu3P. And then we put this little dot here to show that it is connected to 6 waters. Now, why is it 6 waters? Well, hexa means 6, hydrate means water. Now, when this hydrate decomposes, all that's going to happen is the ionic compound and the water are going to unbond from one another. So one of your products is going to be Cu3P without oxygen or water connected to it. And the other product is going to be water, which is now by itself. So when you balance this, if you have one of the hydrate, you have one of the ionic compound, and then you're going to need however many waters you had in the hydrate. But you could have trihydrate, you could have tetrahydrate, you could have decahydrate. So you can take any one of those molecular prefixes and stick it on hydrate, and that tells you the number of waters in the hydrate. Now, the next type of exception we're going to cover has to do with single replacement reactions that involve water. So if we were to drop, for example, lithium into water, and you were to predict the products of this single replacement reaction, my guess is you would go to the activity series of metals. You'd see, does lithium replace hydrogen? It will. And my guess is you would say, all right, well, lithium's going to bump hydrogen off. So we're going to get H2, and then we would get Li2O. That does not happen, which is why this is an exception. If you ever see the single replacement reaction of a metal with water, you can't consider water to be H2O. What you have to consider water to be is HOH, where hydrogen is the positive ion and hydroxide is the negative ion. So when lithium bumps hydrogen off, which it will, you're going to get hydrogen, H2, because it's diatomic. But you are not going to get lithium oxide. You're going to get lithium hydroxide, which would be LiOH. Lithium's +1, hydroxide is -1, so we can leave the formula like that. So my suggestion to you is, if you ever see a metal reacting with water, don't write water as H2O. Write water as HOH. The hydrogen's going to get bumped off, and you're going to have that metal with hydroxide on the other side. So just be careful of that. The last exception that I'm going to teach you guys is, or has to do with, double replacement reactions. Now, sometimes in a double replacement reaction, we get the formation of a diprotic acid. So this is a product. Now, diprotic acid, there's a couple of things you need to understand here. An acid means we have a compound that starts with hydrogen. So acids are compounds that begin with hydrogen. Diprotic, di means two, protic refers to hydrogens. So a diprotic acid is an acid that has two hydrogens along with the rest of whatever it is. So if you ever get a diprotic acid produced in a double replacement reaction, that diprotic acid is going to break down even further. And I'm going to show you a couple of examples here. So if we take sodium sulfite plus hydrobromic acid, we're going to get a double replacement here. So what's going to happen is sodium is going to go grab bromine, hydrogen is going to go grab sulfite, and you're going to get NaBr plus H2SO3. Now, this right here is what we refer to as a diprotic acid. It begins with hydrogen. It has two hydrogens, and it's got a polyatomic ion there. So here's what's going to happen. If you ever have a diprotic acid, you're going to still get our NaBr as a product. But that diprotic acid is going to decompose into H2O and whatever is left. So if we remove two hydrogens and an oxygen from this compound, we're left with SO2. So whenever you get a diprotic acid produced, you must write it like this, and you must break it apart and then balance the equation. Another example would be Na2CO3, sodium carbonate, plus hydrochloric acid. Sodium is going to go grab chlorine, so you're going to get NaCl. Hydrogen is going to grab carbonate, so you're going to get H2CO3. Again, this is a diprotic acid, so we're not going to write it as H2CO3. We're going to pull H2O out, and then we're going to put whatever's left. So I'm just going to erase this, and I'm going to put H2O plus CO2 would be left over.